Hi everyone, I'm Xue Zhang from Peking University. Today I'm going to talk about the paper Characterizing Adversarial Defects of Deep Learning Software from the Lens of Uncertainty. Over the past years, we have witnessed the success of deep learning in a variety of applications, such as autonomous driving, manufacturing, smart devices. Like traditional systems, deep learning systems also suffer from vulnerabilities. One typical representative is an adversarial example. When we make a small perturbation to the original image, the deep learning system can make a different prediction while human could still recognize the image very easily. Such decision errors, for example in autonomous driving scenario, could lead to severe consequences. Basically, a well-trained DL model is a function mapping an input to a probability distribution over a set of labels. For instance, in this cat-dog binary classification problem, when the output distribution is 90% versus 10%, the model presents the decision cat with high confidence. However, when the case is 40 versus 60, it states that the model has same features of both dog and cat and thus presents the decision dog with relatively low confidence. The prediction confidence actually reflects the distance to the decision boundary. The data points near to the boundary are those the DL model is not confident about. We can see that the prediction confidence is a natural representative to characterize the behavior of DL models on different inputs. Normally, we use a single well-trained model with fixed weights to help us make decisions. Bayesian framework regards the weights as random variables, obeying a distribution. We can do predictions on a set of models with sampled weights from the distribution. The variance of the outputs characterizes the uncertainty behavior of the inputs. For example, when we feed a cat image to the sampled models, the outputs demonstrate small variance. This indicates low uncertainty towards the input image cat. When we feed a bird image to the sampled models, the outputs demonstrate high variance, indicating high uncertainty. We adopt Monte Carlo dropout to estimate uncertainty measures. It is a practical method and is scalable to large models. We perform multiple forward passes for the same input. With the support of dropout, we get the prediction in different network structures. They comprise an ensemble of models. The uncertainty matrix can be estimated based on the predictions of the model ensembles. Existing techniques, for example the attack methods, only leverage label probability to generate adversarial inputs. Such inputs might cross the fixed boundary and demonstrate a new probability distribution among the labels. Meanwhile, they would lead to different outputs with regard to a range of boundaries. Uncertainty matrix could characterize the variation in the outputs. Therefore, we intend to adopt both the prediction confidence from deterministic execution and uncertainty measures from Bayesian ensembles to characterize the data inputs for further study. This is the overview of our work. We intend to achieve three research goals. First, since there are multiple types of uncertainty metrics, we want to study their ability in differentiating adversarial inputs and benign inputs. Second, we want to characterize the behavior of data generated by existing techniques and identify if there exist any uncertainty patterns. Finally, we try to generate data with uncommon patterns that are largely missed by existing techniques. About the metric study, we collect the prediction confidence and Bayesian uncertainty measures, including the probability difference, variation ratio, entropy, and mutual information. Then we evaluate their ability of differentiating benign and adversarial examples. Based on the empirical study on the metrics, we select the prediction confidence score and variation ratio to characterize the behavior of data inputs. They can be calculated following the formal definitions. The data inputs for characterization are collected from multiple sources. We adopt four attacks: FGSM, BM, DeepFu, and CMW, two testing techniques, TensorFuzz and DeepHunter, to generate the adversarial inputs. The well-classified test data are the benign inputs. We observe that different types of inputs have specific patterns. Benign inputs demonstrate high confidence and low variation. Adversarial inputs generated from attacks have low confidence and high variation. Compared with the attacks, testing tools adopt more mutation strategies. However, most of the data still fall into the category of low confidence and high variation. To this end, we have characterized the inputs generated through existing tools and identified the common patterns they demonstrate: HL for benign inputs and LH for adversarial inputs. Naturally, we would wonder, is it possible to generate data with the remaining uncommon patterns? For example, data with LL and HH patterns, adversarial inputs with HL patterns, benign inputs with LH patterns. We leverage the uncertainty metric as guidance to generate inputs of targeted patterns, following the workflow of genetic algorithm. After the population initialization, we check whether the generated data satisfy the objective of the targeted pattern. If not, we select data with the largest fitness values to perform crossover and mutation. The test generation stops when the objective is satisfied. We design different piecewise fitness functions for different targeted patterns. You can refer to our paper for more details. Here summarize the research questions we conduct experiments to answer. First, we evaluate the ability of uncertainty metrics in differentiating adversarial inputs from benign ones. We use AURC score to measure the separation ability. The results on 3 datasets across 4 models all show that prediction confidence and variation ratio have the best performance from the perspective of deterministic execution and Bayesian execution. Second, we characterize the behavior pattern of data generated through multiple methods. The results show that benign inputs fall into HL pattern and adversarial inputs from attacks fall into LH pattern. Meanwhile, adversarial inputs generated through testing methods mostly fall into LH pattern, but have the potential to provide inputs with more diverse behavior. Third, we leverage the uncertainty metric as guidance to generate test inputs with targeted patterns. The results show that data with the uncommon patterns could be generated by our uncertainty-guided method. We use the L infinity norm to guarantee the validity of the generated data. Finally, we evaluate the effectiveness of the generated inputs in bypassing defense mechanism. For binary classifier and mutation-based defense, the inputs generated from our methods demonstrate strong advantage. For example, it reduced the success rate from about 0.97 to 0.05. On average, compared with the data of common patterns, the generated inputs demonstrate high success rate in bypassing defense mechanism by 35%. That's all. Thank you.